Hey there, so we're continuing our review of general chemistry. This is from the textbook Chemistry and Atoms Focused Approach. I'm using the 3rd edition. Previously, we were talking about the first half of chapter 1, which went over the basics of what is chemistry, and then talked about some of the key scientists that brought about our understanding of the atom. We also went over briefly some basics about matter, physical and chemical change, mixtures, homogeneous and heterogeneous, intensive and extensive properties, and then some different forms of separation, meaning distillation, filtration, and chromatography. In our discussion of matter, we mentioned that matter is defined as anything that has mass and occupies space. And when we consider matter, we need to point out that it can exist in 3 different phases. So either called phases or called physical states. And so those 3 phases are the solid phase, the liquid phase, and the gas phase. And a good way to represent them is if you write them with the gas phase on the top, liquid in the middle, and then solid on the bottom. Then we can also talk about the changes between these phases, called phase changes. And so first we need to define what each of these are. First we have solids. Solids have a definite volume and a shape. Defined volume, defined shape. Liquids have a defined volume but not a defined shape, so they will take on the shape of whatever container they're within. And then gases have neither a defined volume nor a defined shape. You can compress a gas, they will expand to fill the container they're in, so they don't have a definite shape or volume. And so going between these phases, if we're headed this way, solid to liquid, this would be melting. Whereas liquid to solid would be freezing. The most common example that we are familiar with where a single state of matter, we interact with it in all 3 of these phases commonly, is water. We interact with it as a solid in the form of ice, as a liquid drinking water is a liquid, and then as a gas in the form of vapor. And so going between solid and liquid, we have melting. Going between liquid and solid, we have freezing. Going between liquid and gas, we have vaporization. And gas to liquid would be condensation. And then one that we're maybe not as familiar with is just skipping the liquid phase altogether and going straight from solid to gas. This would be called sublimation. And then going the other way, gas to solid would be called deposition. Deposition. An example of sublimation and deposition that you might be familiar with is dry ice, which dry ice is the solid form of CO2. CO2 is in its solid form is very, very cold, and so it's a great freezing agent. But you might notice if you've ever seen dry ice that as it warms up, it doesn't melt. You never see any liquid dripping off of it. It goes straight into a gas. It goes through sublimation, so it goes straight from a solid to a gas as it warms up. And when we're looking at this chart, we can notice that the up arrows, they all mean that we need to add energy to a system. And we intuitively understand this because if we think about a block of ice going from a solid to a liquid, what do we need to get it to do that? We need heat, which is a form of energy. And so to go this direction, solid to liquid, liquid to gas, or solid to gas, we need to add energy. Whereas if we go the other way, we're actually going to be releasing energy. And when we think about energy, we need to think about it in two different ways. We have what's called potential energy, which is abbreviated PE, potential energy, and then we also have kinetic energy. So what is energy? How do we define energy? That's kind of an ambiguous term, but in science, everything has a definite definition. And so energy is the capacity to do work. And that means that we also need to define work. So what is work? Work, which we can represent as a W, is equal to force times distance. So if you think of pushing something heavy, you have to, the push is your force, and then the movement of it is the distance it's going. If you multiply those two values together, you have how much work was done. So energy, the capacity to do work, and then work is force times distance. When we think about physical energy that we expend to do work, that often comes from chemical energy. So within energy, there's a lot of different forms. And especially if you think about like purchasing energy for your home, you know that there's many different ways that energy can be used. And you have electrical energy, but you might notice on your electrical bill that it specifies where the energy is coming from. Was your electrical energy made through nuclear? Was it from solar? Was it geothermal? Then you have combustion reactions. Like in your car is doing work. It's producing force over a distance. And that energy is coming from combustion of the fuel. And so we ourselves, we do physical work. And that energy is coming from chemical reactions. It's also coming from combustion, like a car, just more efficient. And so we can think about our physical energy that we expend to do work. It comes from chemical reactions in our bodies. And one of those main reactions is the combustion of glucose. Glucose is a molecule. It accounts for our blood sugar. That's how it's often termed in the health world. And the energy that is in glucose is what we consider stored energy. So the molecule itself is not doing any work. It's stored energy. And stored energy is the definition of potential energy. So potential energy we can think of as stored energy. Example being glucose. But glucose can then release energy by being part of a combustion reaction, so a chemical reaction that converts the stored energy into actual motion. And the energy of motion is what we call kinetic energy. Energy of motion. And we will learn a lot more about the different specific chemical reactions, one of them being the combustion reaction, but that will be more second semester. In general chemistry, you get into a lot of the different classes of reactions and how they each happen and the energy involved in that. So the energy of motion is called kinetic energy, and then the amount of kinetic energy is the product of the mass of the object times the square root of the speed. So if we want to define this mathematically rather than just via words, we can actually define this as kinetic energy is equal to 1/2 mass times speed squared. So you're wondering how much a moving object has of kinetic energy. So if you imagine an athlete running, and you're like, I wonder how much that running exercise is burning in kinetic energy. You could figure it out by the mass of the object, so in this case, the runner, multiplied by the speed squared. Well, half the mass times speed squared will give you the kinetic energy of that runner. And so this, if we look at this, we can see that if two people were going the same speed, then the one with greater mass would be expending more kinetic energy. But we need to think about another factor when we think about potential energy and kinetic energy, because when we burn glucose, potential energy, to do work such as running, not all of that chemical energy released becomes kinetic energy, the energy of motion. Some of it becomes heat, and heat is the transfer of energy that takes place because of a difference in temperature. And heat always moves from warm to cold. And so if we go back to our example of like your electrical bill, when we as humans are trying to create energy, a lot of thought is being put into how do we get energy from one form to another form as efficiently as possible without losing too much of it to heat. And this is a big challenge. All that we just talked about, the kinetic energy, the potential energy, all of it obeys what we call the law of conservation of energy. And this is a scientific law. As we talked about in the previous lesson, scientific laws describe something we observe, whereas scientific theories try to answer the question why. So this scientific law states that energy cannot be created or destroyed, but it can change forms. Now, it doesn't tell us why it does this. This is an observation that's been consistent and documented and now is a scientific law. And we will eventually learn the why behind this. But energy in all these forms obeys the law of conservation of energy, the principle that energy cannot be created or destroyed, but can change forms. And if we go back to the physical states of matter, the solid, liquid, gas, we can better understand the arrows. If we think about a solid, this form of matter has low kinetic energy. It has low energy of motion. And I don't mean that like the block of ice isn't moving around on your counter. Because if you have a glass of water, it's also not moving around on your counter. But liquid does have more kinetic energy. What we mean is that the molecules themselves in a solid have less movement than in a liquid. As you move up this, the molecules in whatever sample of matter you are considering have more kinetic energy. They have more motion. And so a solid, the molecules are much stiller, less energy in the system. And as you add kinetic energy to the system, it will go through a physical change from solid to liquid to gas. And so as you study chemistry, you will continually be learning about how energy impacts matter and how matter impacts energy. All right. Let's move on to expressing experimental results. At the beginning of chapter 1, the textbook talked about a number of different experiments that led to our understanding of the existence of the atom. And as scientific methods got better in the 18th century, scientists started to really understand that accurate measurement was necessary for exploration, especially in chemistry. Chemistry is focused on tiny things, which means that in order to have any kind of conclusions that are actually meaningful and not just measuring noise, we need very accurate measurements. And this started to actually be possible because the instrumentation was getting better. And so chemistry needed careful experimentation, and that brings about a desire in the scientific community for standardization of units. So since 1960, all throughout the world in the scientific community agreed to use the modern version of the French metric system as our standard of units. And the system of international units, it's called. We often abbreviate it SI units. So what do we mean by units? Units are things like a mile. And they are a standard. So we have defined a distance, and then we can use multiples of that distance to explain how far something is apart. But there are many different units. You have miles, you have feet, you have meters. All of these are units. And so in the scientific community, they wanted to use standard units across all the scientists and units that were very well defined. So that if I said something was 1 kilogram and you said something was 1 kilogram, we knew that we were both using the same kilogram and not that we had just picked arbitrary values. And so in SI units, we have 7 primary units that then all of the rest of the units are based around or variations of. And so for mass, we have the kilogram. For length, we have the meter, which is M. Temperature is in Kelvin, which is K. Time is in the second, which is S. Electrical current is in amperes, which is A, and then quantity, and again, if you hear my dog, he's sleeping next to me, so forgive the huffing and puffing. Quantity of a substance is in the mole, which is abbreviated MOL. And so these are our 7 base standard units. And when we talk about numbers in general, we want to be using useful numbers. And so something that is a part of understanding SI units is understanding prefixes. Prefixes allow us to express very large numbers or very small numbers in a format that is actually understandable for our brain. Like if I write something like this doesn't really have much meaning to us. And also trying to do math with all of these zeros gets really complicated. And so SI units have prefixes. If we think of, let's do the meter. So if we have 1 meter, then we could say, I have 100 meters. But instead of saying 100 meters, we could say that every 100 meters is the same as a hectometer. This equals a hectometer. Or we could say, I have 1,000 meters. But we could also say that 1,000 meters is the same as 1 kilometer. Kilometer. And so suddenly using a 1 instead of a 1,000 can simplify things a lot. And so these prefixes allow us to write things in much more manageable number sizes. So again, prefixes, they indicate a fraction or a multiple of a number and allow us to express very large or very small numbers. And the multiplers, it's all based on a system of units of 10. you can write this out like this. You have these. You can see all of the different prefixes, and different courses require you to memorize different amounts of them. So it's very common to go up to tera and usually down to femto. Sometimes they don't have you memorize these down here. And what I mean by over here, the base tens, this brings up a concept of scientific notation, where when we want to notate where a decimal place is, sometimes we don't just write out the whole number. We write it out as a power of 10. So for example, if I have 100 grams, I could write this out in scientific notation instead as 1.00 times 10 to the 2 grams. And what I'm saying is, usually the decimal point's here. I move this decimal point over 2 places to the left. So a positive 2 means from the normal number to get it to scientific notation, I moved it over 2 places to the left. And so now I have 1 times 10 to the 2 grams. So to go from this backwards, I would be like, to go from the original number to scientific number, a positive exponent means you moved it to the left. To do it going the other way around, you would need to reverse it. So this would mean move it to the right, and we're back to the original number again. So scientific notation is very handy. So positive, if you're on the original number, if you're moving it to the left, you're going to end up with a positive exponent. But you could also move it the other way around. So say I had this number and I wanted to express that in scientific notation. I could move the decimal point instead this way to the right and write this as 1.0 times 10 to the 123 to the negative 3. So when you're looking at exponents, you can very quickly know if there's a negative exponent, you're talking about a tiny number. And if there's a positive exponent, you're talking about a number bigger than 1. So when we look at this, these are just telling us the conversion factor. So say we stick with meter. Right here we have the prefix deci, so a decimeter would be 1 times 10 to the negative 1. So if we have 1 times 10 to the negative 1, what is that really? It's move the decimal point over 1 going that direction. We have 0.1. A shortcut, so it's referring to moving the decimal point, but because of the way we write numbers, you can also think of it as the positive exponent is telling you how many zeros are going to be added. So if you have 10 to the second, that would be a 1 and then 2 zeros. So it's equal to 100. Whereas if you have 10 to the negative second, it's telling you how many decimal places there are. So you have 0.01. And of course, it doesn't have to be once. If I was dealing with 5 grams, like 5 times 10 to the second, that would be equal to, right, a 5 and then 2 zeros, so 500 grams. And this is just a fast way to write out what each of these prefixes mean. You could totally write it out as like, deca means 10, hecto means 100, kilo means 1,000, mega means 100,000. You could write it out with the full number with all the zeros, but scientific notation is a shorthand, and it's going to come up again when we talk about significant figures because it's very important. So I would highly recommend memorizing your prefixes. And you are already familiar with a lot of these prefixes because these are units that we use a lot, like the kilogram. Very common. And you've heard of like terabytes and stuff. And so they show up all throughout the world. So memorizing what the symbol is for each of them, what they stand for, and how to convert back and forth between them is really helpful. And then also converting in and out of scientific notation is a good thing to practice. And there's a lot of practice online that you can look up, just practice sheets that will get you. And once it gets in your head, like I actually struggled kind of explaining it to you because it will get so far in your head that it becomes intuitive and then you kind of forget why, why things mean things. But yeah. Okay. So we've talked about prefixes, and that's a good place to move into significant figures. When we're talking about numbers, we can put them into two classes. We can call them uncertain and certain. And by that we mean certain numbers are numbers that are defined, as in counting. When I have 12 eggs, that's a defined number. Whereas uncertain numbers are numbers that are measured. And so they have human error built into them because I don't know how perfectly you measured it. Like the instrument you're using might only have measurements to a certain decimal point. And so you can only get it so exact. And so uncertain values are measured values, whereas certain values are what we call counted, defined, or exact values. For example, there are certain mathematical numbers that are defined and are known to an infinite amount of decimal points, like the number pi. So that's an exact number. And so when we are doing scientific calculations, we need to know the difference between certain numbers and uncertain numbers. And that's because we want to be able to express how accurate a number is, how well we know that number. Which brings up the concept of accuracy and precision, which sound very similar, but in science they are defined as two distinct things. And so a good way to think of it is if you were shooting at a bullseye with an arrow, the closer you hit to that bullseye, that means the more accurate you are. Accuracy has to do with the agreement between an experimental measured value and the true value. So in the terms of arrow, it's an agreement between where the arrow hits and where you're trying to hit. And the closer those two things are, the more accurate you are. Precision instead has to do with how close the different measurements are. So if I took a measurement 3 times and I got the same number each time, I would be very precise. It might be nowhere near the true value, what I was trying to measure, but all the measurements agreed with each other, it would be very precise. So in terms of shooting arrows, it would be like if you shot 3 arrows super close together, but they were like all the way at the edge of the target. They weren't anywhere close to the bullseye. You were not very accurate, but you are very precise. You got them all in the same place. You're very consistent. And so precision and accuracy are two different things, which brings up the idea, how do you even check for accuracy? How do you know what the true value of something is? And chemistry, we use things called standards and calibration, where we check our instruments against something that is known. So say we have a scale, and we want to know how accurate our scale is, we could take a weight that's been defined as a certain number and we could put it on our scale and we could see what our scale read, how close it was to the actual value, and that would tell us how accurate it was. This concept brings us to the idea of significant figures. How do we express how well we know a result of a measurement or calculation derived from those measurements? There is a big difference if I tell you, if I measure something and I measure it to the closest foot versus if I measure it to the closest inch, right? One of those has a lot more wiggle room in it than the other. One is much more defined than the other. And so when we write down numbers, we need a way to express how well we know the result. For example, again, my scale reads to 2 decimal points. If I wrote down a number with a 3rd decimal point, I would be making up that number. And you would think that I knew how much I weighed to 3 decimal points. And that's not true. I know it to 2, and I made up the next number. So significant figures tells us how well we know a number. And we need, when we do calculations, we need to be able to carry that understanding through our calculations, so the answer we then produce is giving that same kind of precision. We're trying to express the certainty to which we know a value. So when we talk about numbers, one difficulty is that with zeros, sometimes they're significant, meaning that they tell us how well we know the value. And sometimes they're just holding a placeholder. And so we need to know when zeros are significant and when they are not. So there's a few rules. The first rule is when we have a 0 at the beginning of a value, it's never significant. So an example being 0.0592. Zeros at the beginning of a value are never significant. They're just making the numbers end up in the right placeholders. And so if we looked at this number, not significant, not significant, 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 significant. And so we would say this number has 3 significant figures, which we're just going to abbreviate SF. So that's rule number 1 for zeros. Zeros at the beginning of a value are never significant. They're just holding a place. 2, zeros after a decimal point and after a non-zero digit are always significant. So an example being 3.00 times 10 to the 8th. These zeros are after a decimal point and after a non-zero digit, so we know they are significant. So we have 1, 2, 3 significant figures. Third, zeros at the end of a value with no decimal point could be significant, but they also could not be significant. So this is why scientific notation is very helpful. We talked about writing numbers with exponents. It's so that we can express to the accurate significant figures. For example, so again, we said zeros at the end of a value when there's no decimal point could be significant, but they could also not be significant. So an example being 96500. Does this number have 1, 2, 3 significant figures? Or does it have 1, 2, 3, 4, 5 significant figures? We don't know. But if we wrote it instead, 9.6500 times 10 to the 4th, suddenly rule number 2 applies, where zeros after a decimal point and a digit are always significant. So now we know it's 1, 2, 3, 4, 5 significant figures. Or we could write it 9.65, drop the zeros, times 10 to the fourth, and we would know that it just has 3 significant figures. So scientific notation is very helpful in areas where the zeros are unclear if they are significant or not. And then finally, the fourth rule concerning zeros is zeros between 2 significant digits are also significant. So for example, 101.3, this 0 is between 2 other non-zero digits. It is always significant. This has 4 significant figures. Okay, so now we need to talk about when we do calculations. When we do calculations with multiple numbers, each of those numbers has a certain amount of significant figures, and then we need our answer to also reflect that. So when we talked earlier, we talked about measured numbers and defined numbers. When we are trying to figure out the significant figures of an answer, we are just paying attention to the measured numbers. The certain numbers, the ones that are defined, we don't need to pay attention to those because they have no uncertainty in them. So we don't need to carry on the uncertainty. They are their own thing. So if you have a measured number, like the density or something that's a measured number, density, you need to pay attention to the significant figures. But then if you have multiplying it by something that you've counted, like the density of the eggs multiplied by 3 eggs. 3, you don't need to pay attention to the significant figures. If you were multiplying some density times number of eggs, you might be tempted to be like, oh, 3, this is a 1 significant figure number, and that's going to play into my answer when I write down how many significant figures there are. No, this is a counted number. We just ignore it. Okay. So we're going to talk first about multiplication and division. When we do multiplication and division, the answer that we then produce, we're going to round that answer to match whichever value in the numbers we were working with had the lowest amount of significant figures. So if we have an example 6.00 divided by 420.00, we can go back to our rules about zeros. This one, decimal point, and a non-zero digit, so we know all of these are significant. So we have 4 sig figs, and then same thing here, we have 5 sig figs. So we're going to do this calculation, and we end up with 0.142857. Our calculator is just going to produce a whole bunch of digits, but we know that not all of those are actually real. They're just mathematical. They don't come from any measured certainty. And so we need to round this number to match the amount of certainty we have in these numbers. And so we learned that multiplication and division, we round to the lowest significant figure of the inputting numbers. If you had a calculation that was quite long, so like a whole word problem, and you were going to multiply and then divide and then add, you wouldn't want to do any rounding until the very end so that you don't lose any digits. So that's just a note. These are just a one-step process, so we're going to look at the answer and round immediately. But if you were doing a longer calculation, you would wait until you got to the end. So which one of these has less significant figures? Oh, we forgot to write this down. We have 5 sig figs and 4 sig figs. 4 is the smaller amount. So that means we need to round this number to have 4 significant figures. So 1, 2, 3, 4, we need to round to this decimal point. We have a 5 after that, so basic rounding rules means that we round this to a 9. So our answer is 0.1429. 4 sig figs matches our lowest number. So that's division. Same thing applies with multiplication. Say we had 0.087400 times 11.4. How many sig figs are in this number? We know that before decimal point, this is not significant. So we have 1, 2, 3, 4, 5. Oh, no, 6. No, yeah, there's 5. my brain is prissing around. Okay, this has 5 significant figures. Why is that? Because remember rule number 1 about zeros is zeros at the beginning of a number are never significant. Now these would be significant if there was a non-zero number before it, but there isn't, right? There's only zeros. So neither of these are significant. So we have 1, 2, 3, 4, 5 sig figs. And then this one we have 1, 2, 3 sig figs. So if we do the multiplication, we're going to get an answer of 0.99636. But we need to round this to 3 significant figures. So instead, we're going to write down 0.996. 3 sig figs. We rounded it just to a 6 because the 3 is less than 5, so we don't round up. Just stays the same. So again, multiplication and division, we're rounding to the lowest significant figure value. Now, with subtraction and addition, we're not going to count the total amount of significant figures. Instead, we're going to round to whichever number has the lowest amount of decimal points, the lowest significant figures within the decimal points. So, an example being, if we have 2.5271 plus 126.01, what would this be? So a great way to line this up, you could count significant figures in the decimal point. Here we have 1, 2, 3, 4. Here we have 1, 2, so we know our answer is going to have 2 decimal places. This is the smaller amount. You could also write this like this, 126.01 and then 2.5271. Line up the decimal points. So we'll get our answer as 126.5371. And we're just going to draw a dotted line. Smallest amount of decimal points. Everything after that we don't keep. So here we have 128.53, but we need to round this up because there's a 7 after. 128.54 is our answer, which has the correct amount of significant figures. Okay, so finally we need to talk about unit conversion. Unit conversion is vital to chemistry and something that will show up all throughout your life. And what we mean by that is, what if we have a value in one unit that we want to get to another unit? Say that someone tells you how fast they went in miles per hour, and instead you want to know how fast they went in kilometers per second. How do you get from one to the other? So to do that, we use what we call conversion factors. And a conversion factor is a ratio of equivalent units expressed as a fraction that allows us to convert between units. So if I was trying to get from miles per hour to kilometers per second, I need to know what is the conversion factor, how many miles are per kilometer. What is that factor that correlates these two numbers? I also need to know the current conversion factor of hours to seconds. How many seconds are in an hour? That ratio, that fraction is called a conversion fraction. And so when we write these out, we can write them with all their units, and we use the conversion factors, And if we line it up correctly, we will end up with the units we started on, a bunch of conversion factors, and then the units we wanted to get. And in order to do that, we're going to line them up as fractions. And so if we start with something with our initial units, and then multiply it by a fraction of desired units over initial units, these units will cancel out and you'll end up with an answer in your desired units. So that's kind of vague, but let's do an example like we said. So if we have 60 miles per hour, we can write this as 60 miles on the top over 1 hour. That's what miles per hour means. You're going 60 miles in an hour. And now we want to get hours to seconds. So how many seconds are in an hour? There's 60 seconds in a minute and 60 minutes in an hour. So we could go 60 minutes an hour, 60 minutes an hour. Oops, but we want to switch this. So instead, minutes is on the bottom and hours is on the top. And when you have units that one is on the bottom and one is on the top, they cancel. If you'll remember fractions, that's from that. So instead, we need to write it as 1 hour is equal to 60 minutes. Now we need to get minutes to seconds. So we know that times 1 min is equal to 60 seconds. And then we need to get miles. What did we want to convert it in? Meters? Let's go miles to meters. So we need to know how many meters are in a mile. So let me write this out again so that we didn't run out of space. We have 60 miles per hour. Then we have a conversion factor of 1 hour over 60 minutes. Gets us converted to minute, but then we need converted to second. So we need to put 1 min is 60 seconds. And at that point, we've canceled out our units and gotten us to seconds, but we're still in miles per second. So we need to get from miles to meters. So we can look up how many meters are in a mile and use that as a conversion factor. 1609.34 meters per mile. So we would take 60, we would divide it by 60, we would divide it by 60, and then we would multiply it by 1609.34. And our hours cancel out, our minutes cancel out, and our miles cancel out. And so we would be left with meters per second. And so that is a unit conversion. And these conversion factors, like how many meters are in a mile, how many pounds are in a kilogram, these are listed in your textbook. And some of them you will start to memorize. An area that we're not going to talk about today, but is like how to convert between the different kinds of temperature scales. We briefly touched on in standard units, SI units, that we use the Kelvin scale. But probably you're familiar in your everyday life of using either the Fahrenheit or the Celsius scale. And so converting from temperatures is also a vital thing to learn. So a couple topics that are in this chapter that we did not go over is we didn't talk about scientific notation expansively. And maybe I should do one just on scientific notation because I feel like my description was not very good. But there's more of that in the chapter. We also didn't very thoroughly talk about the different temperature scales and how to convert between them. And then the final section of the chapter is about experimental results. So that's topic 1.9. And I'm not going to go over that because I feel like at this point, with so little context of how scientific experiments are performed and how to do the calculations. These definitions just kind of don't mean anything. But if you want to read about them, it talks about standard deviation, confidence intervals, outliers, and Grubbs tests. And these are useful mathematical calculations that we have to analyze data and values and express how well we actually know that value. Like, how much are we guessing when we say this number? And then we use other numbers to tell each other that. And it's very important to understand these concepts, but they will come up again later in the course, and I feel like they're easier to understand once you have some other knowledge behind you. So that brings us to the end of chapter 1, and then the next chapter is chapter 2, and we're going to talk about atoms, and things start to get really fun. All right, bye.